How much do you know about circular polymers? Well, today I will give a brief history on how they were discovered and synthesized, as well as compare them to linear polymers and their benefits or disadvantages to circular polymers. I will also discuss their unique properties and their potential applications for the future. Let's begin with the history. In 1894, the first synthesis of a circular polymer was done by Emil Fischer. He designed a reaction with an amino acid and a carbonyl compound, such as a diketone, to form a lactame ring. Hydrolyzing the lactame ring then produced a cyclic polypeptide. Emil Fischer was awarded the Nobel Prize in Chemistry in 1902 for his many contributions to the scientific field. Later, in 1930, W.H. Carothers pioneered the synthesis of circular polymers by a method known as ring opening polymerization. He took cyclic carbonate esters and combined them in a process he referred to as an ester interchange, as seen above, where the ester groups of the two molecules would combine, forming a larger ring molecule. His method would later lead to the ring closure and ring expansion synthesis methods used today. In 1964, Barbara Chandler discovered that specific types of DNA existed as circular polymers. She examined DNA from Phi-X174, which is a bacteriophage virus that infects E. coli. She found that the bacteriophage was resistant to heat and hypothesized that the circular structure helped in the strand selection process during transcription. An example of the DNA can be seen above by an electron micrograph experiment. G. Schill and A. Letteringhaus in 1964 synthesized the first microcycle polymer known as catenna, a type of polymer consisting of interlocking rings, as seen above. Fraser-Stoddart in 1990 further progressed the idea of interlocking rings by exploring new ways to synthesize and manipulate interlocking molecules. Some examples of the molecules he was able to create and interlock are shown above. Recently, a company known as Sabic produces circular polymers by using recycled, low-quality plastics that would otherwise end up as pollution. The recycled plastics are tuned into circular polymers that are used in a variety of applications, such as food packaging and personal care products. Now let's take a look at the difference between linear and circular polymers and why they might be of interest. In order to understand the difference, we need to be able to model the material's behavior and properties to better understand their potential applications. To study their properties, like the rheological and viscoelastic properties of linear and circular polymers, we need to comprehend the behavior of the chains and chain interactions. Linear chains have free ends and undergo something called reptation, which is considered a snake-like movement. A representation can be seen on the left. D. Gen first proposed the reptation model, and later Doyd-Edwards further extended the reptation idea to be confined to a tube-like model. However, circular polymers did not follow the same principles as the linear polymers did. There are different models to explain the dynamics and conformation of circular polymers, as seen on the right. Two common models are known as the lattice animal model and the double-folded linear model, which both try to imitate how cyclic molecules or cyclic polymers move. For instance, the double-folded linear model suggests that double linear conformations are formed. According to these models and experimental techniques, linear and circular polymers show very different behaviors in their topological, physical, and rheological behavior. The topology difference between linear and circular polymers is straightforward. Linear polymers are monomers connected end to end, forming a straight line with open ends, while the ends of circular polymers are connected, forming a ring-like structure. The thought of entanglement is thought to directly correlate with the presence of end groups. For instance, since linear polymers have chain ends, there is more entanglement occurring than in circular polymers with no chain ends. It is worth noting, however, that if you have a combination of linear and circular polymers, this may lead to even more entanglement. These topological differences lead to physical differences in the material's properties. Linear polymers tend to show a lower glass transition temperature, slower crystallization kinetics, and a higher hydrodynamic volume, while circular polymers tend to have a higher glass transition temperature, faster crystallization kinetics, and a lower hydrodynamic volume. Using rheological techniques, it is also shown that linear polymers have a higher intrinsic viscosity and a higher melt viscosity than circular polymers do. Taking a closer look at the glass transition temperature of a cyclic and linear polymer known as poly-TCDVE, we can see that the glass transition temperature of the circular polymers is higher than their linear analogs. It is also shown that the glass transition temperature of circular polymers is less dependent on molecular weight than the linear polymers are. This was attributed to the fact that circular polymers have a comparatively smaller free volume than linear polymers due to linear polymers having free ends. Lastly, circular polymers were shown to have a faster crystallization rate than linear polymers. They performed polarized light optical microscopy on linear and cyclic forms of polycaprolactone, or PCl for short, and indicated that the cyclic variation had faster nucleation and growth rates than the linear variation. This finding was accredited to the fact that cyclic variation had a lower melt viscosity than the linear analog. So how are circular polymers synthesized to have these unique properties? There are two main methods used today for synthesizing circular polymers. Either the ring closure method or ring expansion method. The ring closure method can be done by the bimolecular or unimolecular approach. First, we will discuss bimolecular ring closure method. The bimolecular ring closure involves a reaction between a bifunctional polymer and a bifunctional coupling agent, as seen on the top of the screen. Each end of the polymer and coupling agent attach to each other, forming a ring on the left. Unfortunately, different combinations of polymers and coupling agents can attach together, forming linear impurities, or different sized rings, as seen on the right. This leads to low yields and large dispersity in ring sizes. Therefore, bimolecular ring closure is performed in low concentration to minimize these side reactions. Unimolecular ring closure involves a bifunctional polymer with two different end groups, which eliminates the need for a coupling agent. This also eliminates the concern with stoichiometric ratios between the polymer and coupling agent that could lead to excess polymer or coupling agent. Again, linear impurities in various ring sizes can occur, so the reaction should still be performed in low concentration. Another fact is the molecular weight. The higher the molecular weight, the harder it becomes for polymers to find its end. It's also worth noting that it is more difficult to synthesize bifunctional polymers where both ends are different. The last method, the ring expansion method, addresses the low concentration issue with the other two methods by using an initiator molecule and circular monomer units. However, the reaction is difficult to control to get uniform ring sizes. So this method has a higher dispersity than the others. On the other hand, there are lower linear impurities. Linear impurities still exist due to the weak bond of the initiator molecule breaking. Overall, there is no best method for synthesizing circular polymers. It depends on the purpose and application of the circular polymer. If you want less linear impurities, or you want a smaller dispersity in ring size. So let's take a look at the advantages of circular polymers. Circular polymers show an increase in their stability. For instance, circular polymers have a higher glass transition temperature and melting temperature with a higher resistance to degradation. They also show an ability to withstand radiation longer than linear polymers. As we already mentioned with the company Sabic, circular polymers are recyclable to form functional products and applications like household care items, making them more eco-friendly. The cyclic structure of circular polymers also provides opportunities for functionalization, allowing for the introduction of new properties and applications in the future. Furthermore, circular polymers are generally more soluble in common solvents than their linear counterparts, making them easier to process and manipulate. Circular polymers tend to have better mechanical properties, such as higher elasticity and toughness than their linear counterparts. Overall, circular polymers offer several advantages over linear polymers and have the potential to contribute to the development of more sustainable and efficient materials. Although circular polymers do have their advantages, they also have their disadvantages. The synthesis of circular polymers can be more complex and challenging than linear polymers. The cyclic structure requires specialized techniques and strategies that can be difficult and time-consuming to develop. Also, the unique physical properties of circular polymers, such as their higher glass transition temperatures, can make them more difficult to process and manipulate compared to linear polymers. The complexity of circular polymer synthesis can result in higher production costs compared to linear polymers, which can limit their commercial viability, as well as circular polymers may not be compatible with some existing processing methods and equipment, which can limit their use in certain industries. While some circular polymers have been shown to be biodegradable, many are not, which can limit their sustainability and environmental impact. This is why companies like Sabic right now are using circular polymers as recyclable. Circular polymers are still a relatively new and emerging class of polymers, and their availability may be limited compared to more established linear polymers. So how are circular polymers being utilized today? Circular polymers have been used in the development of biomedical devices, such as drug delivery systems and tissue engineering scaffolds. Their high elasticity and biocompatibility makes them attractive for these applications. Circular polymers can be used to develop high-performance materials, such as composites, coatings, and adhesives, due to their high fracture toughness and resistance to deformation. The high thermal and electrical conductivity of some of the circular polymers makes them useful in electrical and electronic applications, such as insulators, semiconductors, and printed circuit boards. Circular polymers are used in the production of packaging materials, such as films and containers, due to their barrier properties and ability to maintain their physical properties over time. The high mechanical strength and durability of circular polymers make them useful in the automotive and aerospace industries, where they can be used in the production of components such as engine components, body parts, and lightweight materials. What do you think the future of circular polymers will be? Circular polymers offer potential for more sustainable packaging, used to develop high-performance materials for energy storage, such as batteries and supercapacitors. They can also be used in the 3D printing applications due to their elasticity and durability. Further research is being conducted to develop biodegradables from packaging to medical devices. No matter where circular polymers will benefit us the most, their unique properties make them of interest. Thank you for listening.